Welcome back. In the previous class, we have discussed metamaterials, what are they and how they are significantly different from their natural counterpart. Today, in the quantum biophotonics series, we are going to discuss how to apply metamaterials as biosensors. We have seen several examples, or there exist several examples of metamaterials in different application, communication, antennas, cloaking devices, displays. But here in biophotonics, we are more or less interested about the applications of metamaterials as biosensors. So, let us go on with it. What we try to do, we try to modify the shape of the split ring resonator into making something which we call as the asymmetric split ring resonator, ASRR. What is an ASRR or asymmetric split ring resonator? It contains not one U or she shaped structure, it contains two. So, two arcs that have the same center of curvature, that has the same center, but asymmetric length. So, the left hand arc is little bit bigger and the right hand arc is little bit smaller, and they are separated by an angle theta between them. This is the unit cell, the schematic, and this is the scanning electron microscope image. The scale is given from which you can understand what are the size, the length, breadth and dimension. They are made up of gold on top of a glass substrate using electron beam lithography system. So, what is the significance of these structures? I told you that the resonance response of these kinds of U-shaped or C-shaped structure, this is split ring. Remember, this is more of a ring which has got splitted, it is broken. So, it is a broken ring. The resonance response, the magnetic resonance response depends on the size, length, breadth and height. So, if you have two C-shaped structure, two arcs of the exact same structure, exact same size, right, then the response of this left hand arc and the response of the right hand arc will also be same. So, the response will superimpose, the response of this is equal to the response of this, and they have superimposed upon each other and has produced an overall resonance response that is showing a peak at 4 to 4.5 micrometer wavelength. This wavelength is specific from biosensing point of view, because all the proteins, the lipids, fats, etc., more or less vibrate in this particular area. You will soon know why it is such. What we did, we kept the left hand arc constant, the size of it is kept constant, and the right hand arc size start getting reduced. We started reducing the size, thereby increasing the angular gap between the left hand arc and the right hand arc. Previously, the left hand arc and the right hand arc were the same. In the next case, the left hand arc were kept constant, we did not touch it, we simply started reducing the size of the right hand arc. So, what happens now? Previously I told you the resonance depends on the size. If the size is same, the resonance is same. So, the resonance of left and resonance of right were also same, because their size were same and they are superimposing. Now, the left hand arc is slightly bigger than the right hand arc. Their resonances are closer to one another, but not the same. So, the big peak that you see here, starts bifurcating, and the difference in the resonance of the two peak starts coming up. Difference in the resonance of the two peaks start coming up when the big peak bifurcates into two peak and one trough. Bifurcates and it divides, it simply opens up. This peak is because of this resonance is because of this, and what is in between? The in between is the most important part, where the resonance response of this and the resonance response of this is same but opposite, and they have cancelled each other. Imagine two wires, two coils containing electric current. They are brought very close to one another, a mutual current flows to one another in both of them, and the strength of the mutual current is so much so, it does not happen in electric current per se, but the strength of the mutual current, think it like that, it opposes the flow of the normal current flowing through it, so much so that it cancels each other. Further reduction makes them two separate resonator, meaning they are not talking among each other. The resonances have to be close enough to couple. This is coupling. This geometry, they are closer to one another, they are talking among each other, they are producing their characteristic shift. But in this particular case, this is a separate arc almost, this is a separate arc, and here you do not see the response of this at all. It has gone somewhere outside and not attaching or not talking among each other, right. In the previous case, the resonance response were closer, not same but similar. There was a time when the response of this was affecting this, the response of this was affecting this. But here there is so much dissimilarity in size that they do not talk among each other, they do not see each other and produce individual resonances. So, we are not interested in this or this, we are interested in this part, the so called asymmetric splitting resonator of a theta of 20 degree. What it does? It basically hybridizes the resonance. Hybridization of resonance means that the left hand arc has a response, the right hand arc has a response, but when they come together, when they couple, they produce a characteristic response which somewhat belongs with its parent left hand, somewhat belongs with the right hand, but somewhat belongs with something that is completely different, that is completely unique in its geometry itself. So, it is like children of parents. A child will resemble certain things from the father, certain things from the mother, but there will be certain property of the child which will be completely unique to her or his own. So, this is something that this geometry is producing, where the response of this gets modified by the presence of this, the response of this gets modified by the presence of this, and this creates this so called trapped mode or the dark mode, or these days they call it bound state in continuum, different meaning, and there is a slight amount of difference between all of them. I ask you to figure it out yourself because they are simply for me semantics. Overall, what happens is that this is the peak where the response, this one is resonating, the dominance, the resonance of this is dominating the entire system. This is the peak where the resonance of the bigger arc is dominating the system. This, on the other hand, the trough, the dip is the one where the resonance of both are equal and opposite and they cancel each other. The resonance response cancel each other, meaning the light that is given to shine on it cannot transmit, cannot reflect. They are simply cancelling each other. Electric field and magnetic field of this is equal and opposite to the electric and magnetic field of this, and they have almost neutralized each other, cancelled each other, and thereby there is no movement of light. You have trapped light, like you can trap water in a bottle. If you have trapped water in a bottle, the water cannot evaporate, cannot leak out. Here the optoelectric field is trapped within the contours of these nanostructures. I give you the size of this. If the entire scale is 500 nanometer, how thick these are. So, you are sending infrared light of 5 micrometer, compare this with 500 nanometer or 100 nanometer. I told you this has to be much smaller than that. So, you can produce this unique properties of light, where light is simply dissipated or absorbed at a particular frequency depending on the size of the structure that you have created. These structures were all created by me. If I can create, you can create yourself. These are all experimental results. I am not showing you any theory. These are all experimental results made by, created by my own hand, and I can help you create it if you so choose. So, think about it, what purpose you will use this for. You have trapped light or you have resonated light at a particular frequency, at a particular wavelength. In previous class you have seen in the visible frequency range. Here we are doing it in a infrared frequency range, mid infrared frequency range. If you want to go into detail, please go through this paper. It's quite popular these days, this paper. So we utilized it for biosensing. This electromagnetic hotspot, this area is called electromagnetic hotspot because most of the electromagnetic field is concentrating on specific areas, right? There are less amount of electromagnetic field here. They are concentrating at the edge of the arcs, inside, etc. So you can call it electromagnetic hotspots. Heterogeneous distribution of electromagnetic field. Electromagnetic field is not uniformly distributed, it is closer to certain areas. They are metallic structures, so you know antenna effect, you have those tridents like thing in very tall buildings which attract the lightning falling into that particular place and it discharges it. So same thing, electromagnetic field will be concentrating at the end of the arcs or near the metallic plates or the metallic nanostructures. So they can be considered as electromagnetic hotspot. The property of these electromagnetic hotspots are they are very susceptible to any refractive index change. Remember the formula of metamaterial from previous case, the epsilon c, it depends on epsilon c. Any change in epsilon c, the response, this resonance response will change. What we did, we tried to cover the entire material with very thin layers of organic compound like polymethyl methacrylate. This produced more hotspots than its symmetric counterpart. Symmetric counterparts hardly produces any hotspots, but this produces 2 peaks and 1 trough. Now you cover the entire structure with thin layer, thin as in 110 nanometer of PMMA, that is enough to disturb, that is enough to create a refractive index change of 0.49 or 0.4, which results in redshift. This amount of redshift, how much the response have changed because of the presence of PMMA, can be corroborated with the amount of PMMA present. That is your biosensing. Remember previous lectures, what exactly is biosensing? With analyte, without analyte, how the transducer will change its property. We are changing the transducer's property, where this is your transducer. It was previously resonating at say blue light, now you have covered with something else, the refractive index change has happened. Previously light was coming from air and hitting that material, now light is coming from air to the analyte and then hitting the material. So there is a loss for the light that results in redshift. Redshift means loss of energy, that is exactly what it is. So this is the redshift of resonance with respect to thickness. We were able to measure up till I think 30 nanometer of thin films, 30 nanometer. Can you imagine the width of human hair is around less than few millimeters, so around 800 microns, 200 to 800 microns is the width of a human hair, 10 to the power minus 6. 30 nanometer is 30 into 10 to the power minus 9. How many of them can be detected, can be seen, can be understood? We were able to see it with polymethyl methacrylate. But same material can have different refractive index depending on its thickness. Different material can have the same refractive index. So how do you know? Simply by refractive index, how do you detect something? Well, fact of matter remains that most nanomaterials, most organic compounds have their own molecular resonance at particular frequency. I told you this before. Most molecular material have their vibrational frequency in the infrared region, and that is what is determined by spectroscopic methods. You cannot change that, that is fingerprint, that is signature. But with your metamaterials, you can change the size, shape, etc. of your split ring resonator, and you can match those two. The molecules are resonating at this frequency, the metallic nanostructures, the split ring resonators are resonating at this frequency, you combine them together, you get a huge frequency, you get a combined resonance frequency, and this is exactly what we did. We changed the size, the diameter of the split ring resonators, and we started showing this characteristic feature, this carbonyl bond. The previous carbonyl bond, which was at 5.5, got enhanced by the presence of this peak. We can put it either in the peak or in the trough. So, this particular peak is the signature of the material. This redshift, this delta lambda, the gap between black and red shows how much it is. This is what it is. This peak is unique to polymethyl methacrylate. This shows how much of polymethyl methacrylate is. Not only you need to know what is present, you also need to know how much of that substance is present. We were able to do the same thing. So, these are basically the concepts that I tried to cover for today: asymmetric split ring resonators, resonance hybridization, trapped mode, and thin film sensing. I will discuss this in the next class as well. Those of you who are interested, please go through this doctoral thesis of mine that is available free of cost online, and there are beautiful pictures, and if you are interested, you can read a bit more about it. Thank you very much.